This is lecture 9 of the course Engineering Mechanics. In this lecture, we are going to solve an example problem. In this problem, we have an assembly of rigid bodies. There are 3 rigid bodies. Those have been marked RB1, RB2 and RB3. This assembly is constrained from 2 different sides. If we look at the right hand side, one of the members of the assembly is constrained by a pin joint at D. On the other side, the member OA of the assembly is constrained by another pin joint at point O. If we read the problem statement, it says that the members OA, which I am calling as RB1, and member DP, which I am calling as RB2, rotate at constant rates of 2 radian per second and 3 radian per second in the directions shown on the figure itself. The pin at P can slide in the circular slot of radius 4 meter in plate AC. The circular slot is on the plate AC. This is the circular slot. And this pin P, where P is a part of RB2, can slide on the circular slot of radius 4 meter. We are being asked to find the angular acceleration of plate AC, which I am calling as RB3. The other relevant geometric details are given in the problem. This problem is distinctly different from the problem that I solved in the previous lecture. There, in lecture number 8, I had a problem which did comprise of a number of RBs. However, that assembly of RBs in the previous problem was constrained only in one direction. It was pinned to the ground frame. The other side of the assembly was free, and then on that other side there was a point A, and we were asked to find the velocity and acceleration of that point on one side of the assembly. In contrast, in this problem, we have an assembly which is constrained on 2 sides, and what we are being asked to find is the angular acceleration of one of the RBs in this assembly. So it is the constraint existing on 2 sides of this assembly, shown assembly on the screen, which is different from what we had in the previous problem. So before we start showing the formulation how to solve this problem, Let us translate the information given in the text of the problem statement in terms of the mathematical notations that will be used when we start formulating the solution procedure. So the first sentence says members OA and DP rotate at constant rate of given some numbers are there. Since I have numbered RB1, or rather since I have numbered member OA as RB1, the first piece of information that I want to list here is this is the information. Now the unit vectors of my working coordinate system are as drawn as I am drawing them on the screen right now. So I hat is horizontal, j hat is vertical, and k hat is coming out of the plane of the screen. Now G I am calling as the ground frame. G is the ground frame. So this is one piece of information that comes to me. Further, it is said that these rates are constant. Now this is a planar problem. It means for a ground fixed observer, the angular velocity of RB2 is not changing its direction. It is always pointing outside the plane of the screen. Further, the magnitude of the angular velocity of 2 with respect to ground is also not changing because it is said that the rate is constant, and thus I infer that omega dot 1g should be 0. Similarly, I interpret the information about dp and write these two expressions. First was OA and dp is RB2. So I write omega 2g as minus 3k radians per second. I am writing it as minus because you see that the direction of omega 2g is shown to be clockwise. And using the same argument by which I concluded omega dot 1g to be 0, I am going to write omega 2 dot g to be 0. Then I focus on what is being asked in this textual language. Find the angular acceleration of the plate AC. So plate AC is RB3. They are asking for angular acceleration omega dot 3g. This is what is being asked. Even though it is not written explicitly here, the author's intention is to say find the angular acceleration of the plate AC with respect to ground. And thus I am saying we need omega dot 3g. How do we get this expression? Now there is a general approach that I would like to outline as far as solving this type of problem is concerned. What I mean by this type is an assembly of RB is given, constrained from two or more sides, and we are being asked to find the angular velocity or angular acceleration of one of the RBs in the assembly. This is how I define this type of problem. To solve this type of problem, first step is to identify a point somewhere in the middle of the assembly write the expression of let that point be P. Let that point be P, which I am saying I am identifying somewhere in the middle of the assembly. Write the expression of VPF from one side of the assembly Third step is write the expression of the same particle somewhere in the middle of the assembly from another side. And then match the expressions obtained in 3 and 4. Step 3 and step 4. Step 3 and step 2. This will give you a vector equation or a set of equations and that will help us find some unknowns. In this case, performing steps 1, 2, 3 and 4 will help me find omega 3g. However, if you read the problem statement shown on the previous slide, we are not being asked to find omega 3g. We are being asked to find omega dot 3g, acceleration of 3 with respect to ground. However, these steps, what I have shown here, will be the stepping stone to find this quantity. I will illustrate this fully with my formulation in a little while. But for the time being, I propose these as the first 4 steps towards the final solution. These 3 steps, 2, 3 and 4, I call as the velocity analysis. The velocity analysis of point P. As far as this type of problems is concerned. Once you have done the velocity analysis, we will do what is called the acceleration analysis of the same point. What does acceleration analysis include? The acceleration analysis includes the same steps 2, 3 and 4, but with a difference, and that difference would be, instead of VPF, you will write the expressions for APF from one side of the assembly. Then you will write the expression of APF from another side of the assembly. F or G, I am using them interchangeably. F is same as G. APG and APG. Once you have two expressions for APG from the two sides of the assembly, step 4 would be to match expressions from 2 and 3. Again, that will give us a set of equations with the help of which we can find some unknowns, and the hope is that now, with the equations obtained by matching accelerations, you will be able to find omega dot 3g. And here typically what happens, that before you can solve for the angular acceleration of 3 with respect to g, you will need the information about the angular velocity of the same body 3 with respect to g, which we would have gotten by that time using the velocity transfer relationship. Thus, before doing the acceleration transfer relationship, the velocity, thus before doing the acceleration analysis of point G, it is required to do the velocity analysis also of the same point. So since I have changed quantities here, and that's why I'm calling now steps 2, 3 and 4 will be called the acceleration analysis of point B. Thus, to get angular acceleration of 3 with respect to g, you first need to do velocity analysis of point P, get some unknowns, get the angular velocity of 3 with respect to g, and then you do the acceleration analysis, and we should be able to find the angular acceleration of the body of interest. With this roadmap in our mind, now let us proceed to solve this problem. So P is my chosen point. That's the step 1 I mentioned on the previous slide. Step 2 was to write the expression of VPG from one side of the assembly. So that one side I am taking as the D side. From D side I want to write the expression for VPF or VPG. So D side is this is the body. What is VPF? VPF would be, or VPG would be omega 2G crossed with RPD. That's all. That is VPG. We have RPD known in this case. Geometric information is given. If you go to the previous slide, this is a known quantity. Omega 2G is also a known quantity, and that makes VPG a known quantity. You use the numbers given on the first slide. VPG turns out to be 6J meters per second. Where J is, this is I direction, I hat, this is J hat. Now I want to write VPG from O side. Now from the O side, it is not very straightforward to write the velocity of particle P with respect to ground. And since it is not very straightforward, I am going to invoke the idea of intermediate frame and an intermediate point. I am going to choose the intermediate frame to be RB3 itself, and I am going to choose my IP as point A. And mind you, IP should be a point fixed in IF. And then I will use the velocity transfer relationship which gives me this expression VPG P3. Having written this expression, as usual, I start sweeping from right to left and mark various quantities as K or U. K means known, and U means unknown. If a quantity is known, I will use the numbers given in the problem statement and do the calculations, and I move on. If I come across an unknown quantity, I will have to do additional formulation for that. This is how I proceed. So the first quantity that comes on the right hand side of this equation is VP3, is this unknown quantity. It turns out this is not a known quantity, it is an unknown quantity. However, there is some information after all available what should be the motion of P with respect to 3, with respect to an observer who is sitting here. The information available is that pin P has to move in this slot that has been cut, that has been created on RB3. And at this instant, the way this slot is oriented, the velocity of particle P with respect to this observer fixed to RB3 is got to be along horizontal direction. It's got to be along horizontal direction, tangent to this circular slot. And thus I write VP3 as U times I hat, where U is still an unknown quantity. It is a scalar, unknown scalar. I hope to find this soon, but for the time being I develop my formulation based on the understanding that Vp3 is got to be a vector oriented along I hat. This information is useful. So this is still an unknown. I keep it marked as U. We move to RPA. RPA is of course known. This distance is given in the problem statement. We can go back and check on the first slide. I marked this as known. It is some distance along RPA would be some distance along I hat. It is actually given to be a unity, that distance. So it is just I hat. So this is a known quantity. We come to the next quantity, which is omega 3g, and we realize we don't know omega 3g. Right? We don't know omega 3g. However, the problem being of planar motion, I can still write omega 3g as an unknown, which I am marking as just omega times k hat, with counterclockwise being the positive direction of an angular velocity. Again, I have a situation in which I do not know the vector fully. I know its direction, but the scalar part is an unknown, and I keep it like that. Thus, omega 3g is still an unknown quantity. I am fine with that. I will proceed with this much understanding. I come to VAG. Is VAG known? No, it is not known. To get VAG, I will again write a velocity transfer relationship. With IF being RB1 and IP being 0, I can write the velocity of A with respect to G as omega 1G crossed with RAO. VAG is omega 1G crossed with RAO. Is RAO a known quantity? Yes, it is. Is omega RAO is a vector along J direction, and again the magnitude is given. Magnitude is given to be 2 meters. So it is 2 times J. It is a known quantity. What is omega 1G? Omega 1G is also a known quantity coming directly from the problem statement. We identified that on the first slide itself. So with everything known on the right hand side, VAG is now a known quantity. So I go back here, strike off U, and I write VAG as a known quantity. So in this expression of VPG, which I am getting from O side, you will observe that I have two scalar unknowns. The first scalar unknown is U, and the second scalar unknown is omega. To be able to solve for these two unknowns, I need two scalar equations. Can I generate those two scalar equations now? Yes, the answer is yes. We go back to this expression of VPG. From D side, we actually know the exact value, and then we have gotten another expression of VPG going from O side, the side of O. We are now in a position to match the two velocities. That's what I'll do here. Now I will match 1 and 2, and that matching will lead to one vector equation, and since we are dealing with planar motion, this will imply two scalar equations. This one vector equation has two scalar equations inside it. And those two scalar equations are, in fact, I first write the full vector equation. That full vector equation is J. So we match the coefficients of I. That leads us to minus 4 plus u being 0. We match the coefficients of j, and that leads us to omega being 6 radians per second. And this in turn leads me to u being equal to 4 meters per second. One can verify whether I have gotten these numbers correctly or not. So this completes my velocity analysis. Velocity analysis of point P. And I have two clear outcomes. I know the angular velocity of 3 with respect to g, and I know Vp3. So I can write these outcomes in full vector form. This is what we have now. 6 k radian per second, and Vp3 is known to be 4 meters per second along I direction in meters per second. However, these are not the quantities we have been asked to find. We have been asked to find this quantity, angular acceleration of 3 with respect to g. I will show that these solutions will be the stepping stones before we reach this, before we are able to find the angular acceleration of 3 with respect to g. Now, according to the procedure I laid out in the beginning, the next step is to do acceleration analysis of point P. Let's do that. Acceleration analysis of P. Acceleration analysis involves first writing APG from side D. What is the acceleration of point with respect to g from side D? That is going to be this is what it is going to be. I'm using acceleration transfer relationship where IF is 2 and IP is D. Sweeping from right to left, this is a known quantity, this is also a known quantity, this is also known, this is known, this is also known, In fact, this is equal to 0 based on the problem statement. So the only contributing term is this double cross product term. If you put the numbers given in the problem statement, we get APG from side D as 18 meters per second square. So the acceleration of point P is pointed towards D itself. Okay, so this is first step of the acceleration analysis of point P. Next step is to write APG from O side. Like what we did when we were trying to find VPG from O side, I am going to choose an IF which will be frame 3 and an IP which will be point A. And write APG. Let's see what expression we get. Long expression as usual. Acceleration transfer relationship. Let's verify whether I have written things correctly or not. APG, AG, 0.3G, RPA, 3G, 3G, RPA, 3G, VP3 and AP3. VP3 and AP3, yes. Now again, let's sweep from right to left and see what is known or unknown. AP3 is an unknown. P3 is an unknown. But I know I can express this vector in terms of some scalar unknowns. So right now this is a vector unknown, AP3, but I can write AP3 as I can write AP3 in this form. What is the basis of writing AP3 in this form? So P is as seen from this observer, as seen by this observer, P is following a circular trajectory. This trajectory is actually the trajectory of particle P as seen from this observer. It's a circular trajectory. And if it is a circular trajectory, we know that this particle must be having two components of acceleration, one along its ET and the other along its EN, where ET and EN are the native unit vectors of the path coordinate system. Based on what we have studied so far in this course, we know the component of acceleration of P as seen by this observer. The two components are, along this ET, the component is S double dot, where S is the coordinate of the path coordinate system. We have studied this before. And the component of acceleration along En is S dot square by rho. where rho is the radius of curvature of the trajectory. And indeed it is given here. This is rho. Rho equals 4 meters. So this term, which is S dot square by rho, I am writing as U square R by R. R is the radius of curvature and U indeed is S dot, or the speed of the particle. Which particle? P. Particle P with respect to this observer. Mind you, while doing the velocity analysis, we have already found U. U is a known quantity. When we started solving this problem, we might not have foreseen the importance of U. When I was doing velocity analysis, U came out almost like a byproduct of solving two scalar equations. But now we see that it has importance. It is helping me get at least one part of AP3. The other part of AP3 is along ET here, and that part I don't know yet. I know the direction, it has got to be along I hat, but the scalar part is an unknown, and I keep it like that. I put a placeholder, I put an unknown there. Okay, so one part of AP3 is known, another part is unknown. I still keep this as an unknown U and move on. VP3. VP3 indeed we have found by this time. VP3 is nothing but U times I, and U we have already found at the end of our velocity analysis. Omega 3G. This was not given in the problem statement, nor it has been asked to be found in the problem statement. And yet, we underwent the process of velocity transfer relationship and we got omega 3G. We know omega 3G by now. This is a known quantity. And this is indeed the reason why I said earlier, about 15 minutes ago, that even to get the angular acceleration of 3 with respect to g, we must do velocity analysis first of point P. Velocity analysis gave me this quantity and this quantity, which are now proving useful while I am doing the acceleration analysis. Alright. Moving to the next quantity, known, omega 3g, repeating itself in the expression, of course, known. RPA is known. And then we come to the quantity, the prime quantity of interest in this problem, omega dot 3g. That's what we have been asked to find. And we hope we will be able to set up an equation and find it. Even though we do not know the scalar part of this vector, but we at least know that it should be of this form. It's a planar problem. The direction of omega dot 3g must be along k hat. Thus, I have introduced a second unknown now. The first unknown was this, first scalar unknown was this, and second scalar unknown I have introduced here. So, I still keep it as an unknown. And then I come to AAG. Is AAG known? No, it is not known. It is an unknown. But can I find AAG? Yes, I can find AAG. AAG will be, based on the given information, AAG will be omega 1g cross omega 1g RAO. This is the only surviving term when you write the acceleration transfer relationship for this quantity using IF as 1 and IP as O. You can write the full expression, but this will be the only surviving term. Are we in a position to find this? Yes, indeed we are. This is known, omega 1g is known, omega 1g is known, and thus AAG is unknown quantity. So once I have calculated AAG in this way, I go back here and I strike off U and write here unknown quantity. So now we have an expression for APG, this expression, rather long one. I have an expression for APG in which most of the quantities are known, they are marked as K. Some quantities are marked as unknown. One is here, one is here, another is here. These are unknown quantities, and these unknown quantities I have expressed them in vector form using two unknown scalars. One is A and the other is omega dot. What am I going to do next? I am going to match the two expressions of APG that I have obtained. This is my first expression for APG that I obtained here. Let me call it 1. And this is the second expression for APG that I have boxed in this with this green outline. So I have one here in dark brown outline and I have two here in green outline. I am going to match these two. When I match these two, I will get a vector equation. And that vector equation is a rather simple one that you should get. You should get 18i, which is coming from D side of the expression. And when you match it with the O side, you get these terms. Let us call this equation as number 3. It is a vector equation capable of giving us two scalar equations, and those two scalar equations are when you match coefficients of I on both sides, you get 18 equals minus 36 plus A, and when you match coefficients of J, you get 44 plus alpha adding up. I have introduced a new unknown. That unknown should be omega dot actually. I was earlier using alpha to solve this problem. But these are the two unknowns, omega dot here and A here. So A is here, you get one equation for that, you have omega dot here, you get another equation for that. You go ahead and solve. We get A as 54 meters per second square, and we get omega dot as minus 44 radians per second square. And thus omega dot 3g, which should be omega dot k hat, is minus 44 radians per second square. This is the final answer. One can verify.